Hi folks, how y'all doing? We have a great section for you today. It's on orthogonal projections. Let's go ahead and get started. So we're going to start with two vectors that are both in Rn, and we're going to define what we mean by the orthogonal projection of V onto W. And we're going to give you two definitions here. Here's the formal definition. The orthogonal projection of V onto W is a multiple of W that is chosen so that the distance from V to that multiple is as small as possible. So we look at all the multiples of W. So this is W. This out here would be 2 times W. This over here would be negative W. And then we consider how far they are from V. And the one that is the shortest distance as possible is the one that is directly underneath at a right angle. That multiple, which is roughly about 1/2 of W, maybe a little less than 1/2 of W, that vector right there is the projection of V onto W. And that's how we write it. It's the projection on with V on the same line, and then a little W, the thing that we're projecting onto is underneath them. But using the fact that this is going to be a perpendicular line segment and this forms a right triangle, this gives us an informal definition that's much more useful. Draw V and W so that they share the same tail. Construct a perpendicular line from the head of V through the line L that contains W, and let P be the intersection point of that perpendicular line in L. The orthogonal projection is the vector from the tail of V and W to the point P. So it's that vector right there. And that gives us a different definition that tells us what we're looking for. Because the projection forms a side of the right triangle, we can calculate this using trig. So here are a couple of examples of orthogonal projections. This is similar to the example we just did. In this example, the angle is acute. It's less than 90 degrees. And so when I project V down onto W, the projection is just pointing in the same direction as W. But if the angle is more than 90 degrees, then when I project V downwards, the projection is now pointing away from W. They're still on the same line. There's still a right angle here, but the projection is opposite to the direction of W. And so we would get a negative multiple of W for the projection. And as I was saying, we can solve for this orthogonal projection using trig. So I'm going to go back to this previous example here, and I'm going to draw some stuff on here. If I look at this angle here, the cosine of the angle is the projection or the length of the projection over the length of V. Which tells me that the length of the projection is equal to the magnitude of V times the cosine of the angle. And how do we then get from this magnitude to the actual vector? Well, I need to take W and change it so that the length is the length of the projection. And the way we do that is I first take W and make it into a unit vector by dividing by the length of W. And now that it's 1 unit long, I'll multiply by this length, and then it will be the correct unit length. So I'll take this length and multiply it by a unit vector. All right, let's give this a try. So that's the formula that's on this slide right here. This is the length of the projection, and this is a unit vector. When I multiply a unit vector by the length, I get a vector that has the correct length and is pointing in the direction of W. But we can simplify this even further because we know that cosine is equivalent to dot product under a unit conversion. That cosine is the dot product divided by the magnitude of the two vectors that went into the dot product. And so I'm going to substitute this side for my cosine. And when I do that, the magnitudes of v's cancel. And I'm going to do one more thing. I'm going to combine these together. The magnitude of w, let's say w is the vector ABC, for example. The magnitude of w is the square root of a squared plus b squared plus c squared. But the magnitude of w times the magnitude of w, when I multiply two square roots, the square roots go away, and I just get a squared plus b squared plus c squared. But that's just the same as the dot product of ABC with itself. It's a times a plus b times b plus c times c. And that is just w dot w. And so when I take these two magnitudes and combine them, the square roots cancel, and I just get the dot product. And that's what I have here. So I have the dot product of v and w, I have the dot product of w and w, and then I have one more w that stays outside the parentheses. And this is the formula that we're going to be using throughout the rest of our chapter to calculate an orthogonal projection. It's faster than using cosines because dot products are much easier to work with. All right, let's try an example. I have these two vectors, 3, 0, 2 and 1, 3, 2. Let's compute the projection of w onto v. So the formula is that we dot product both vectors, then we dot product w with itself, and divide these, make a fraction, and then we're going to multiply all of that by w. So let's try this out. V dot w is 3 times 1 plus 0 times 3 plus 2 times 2, and that's 7. And w dot w is 1 times 1 plus 3 times 3 plus 2 times 2, and that is 14. So this fraction turns out to be 7 over 14, and this w is 132. 7 over 14 is 1/2, and so our answer is 1/2, 3/2, and 1. Take all these numbers and multiply them by 1/2. And that's the projection. So we can also do a projection onto a subspace of Rn. So the orthogonal projection of V onto an entire subspace and not a single vector is similar to how we define the projection onto a single vector. It is the vector in the subspace that's chosen so that the distance between these two vectors is as small as possible. I have a picture on the next slide. In this case, we have the subspace W is the span of our basis vectors E1 and E2. E1 is a unit vector in the x direction. E2 is a unit vector in the y direction. Their span is the entire xy plane. I have this vector v that's not in the xy plane, but if I look at all of the possible vectors that are in the plane, and I want the one that's the closest to v, it's going to be the one that's directly underneath it at a right angle. And so this is going to be the projection of vector d, v, straight down onto the subspace W, onto that plane. Now, on the next slide, we have a formula for calculating a projection onto a subspace instead of a projection onto a vector. If our basis for the subspace is an orthogonal basis, then we can calculate the orthogonal projection on the subspace by just doing the projection onto each individual vector in the basis and adding them together. So this is the projection onto W1, the projection onto W2, the projection onto WK, and we just add them all together. But beware, this works only if the basis is orthogonal. So let's try an example. Let's see how this formula works. So we have these two vectors here. They are orthogonal because their dot product is 0. 2 times 0, -1, and +1. That adds up to 0. And so we have the span of these two vectors. And I would like to project V onto W. So what we're going to do is we're going to project V onto W1. And then project V onto W2. And add them together. All right, so the dot product of V with the first vector, 4 times 2 is 8, plus 0 plus 4, 8 plus 4 is 12. Then we dot product W1 with itself. 2 times 2 is 4, 4 plus 1 is 5, plus 1 is 6. And then W1 is 211. And then over here, we're going to take V dot W2. So 4 times 0 is 0, -1 times 0 is 0, 4 times 1 is 4, over W2 times dot product with W2. 0 times 0 is 0, -1 times -1 is +1, plus another 1 is 2, times W2, which is 0, -1, 1. So in both cases, the fraction is reduced to 2. So 2 times 211 is 422. 0, 1, -1 times 2 is 0, -2, +2. We'll add those together, and we get 4, 0, 4, which turns out to be the vector we started with. What does that mean when the projection is the vector we got? It means that the vector v is actually already in the plane, and so the perpendicular line, there is no perpendicular line because the vector is already down on the plane itself. So this is a hard way of proving that V is in the span of W. V is actually in W. Let's try an example where that doesn't happen. Here's W1 and W2. They are orthogonal because their dot product is -4 plus 5, that's +1, plus -1 is 0. And my vector V is 1, 2, 3. We're going to project V onto this plane. So the first thing we'll do is we'll project V onto W1. And then we will project V onto W2. And then we add these together. So V dot W1 is going to be 2 plus 10 is 12. 12 minus 3 is 9. W1 dot with itself. Let's see. 4 plus 25 is 29. 29 plus 1 is 30. Times W1, which is 2, 5, -1. Then V dot W2 is going to be -2 plus +2 is 0 plus 3. And then W2 dot with itself, is 4 plus 1 is 6 times W2, which is negative 2, 1, 1. 9 over 30 reduces to 3/10. 3/10 times 2 is 0.6. 3/10 times 5 is 1.5. 3/10 times negative 1 is negative 0.3. 3 over 6 is just a half. Half of negative 2, 1, 1 is negative 1.5 and 0.5. When we add these together, we get negative 0.4, 2, and positive 0.2. And that's the projection that we get. All right, so we know how to calculate a projection onto a subspace if we have an orthogonal basis. But again, this formula works only if the basis is orthogonal. So what happens if the basis is not orthogonal? That's the thing that we're going to do in the next section in the next video. Thanks for coming. I will see you soon.